In this video, I'm going to talk about parametric equations and curves. These concepts are better explained with an example. Let's consider that there is an ant sitting down on this surface, okay? And it starts to move. It starts going places. Something like this. We would like to find the position of the ant. So let's say this is the position of the ant on the xy plane. We would like to know the coordinate of x and y on this plane. Now, how can I do that? We could think of it as a function. So can we express y as a function of x? Can we do that? This is our natural inclination to do. I'll show you very quickly that it is probably not going to happen. Why? Let's look at this x and y. This is my xy plane or Cartesian plane. Let's consider this point. Let's say x equal to 1 or something. Okay, this is your x. And if you draw a vertical line, you can see that it fails the vertical line test because it intersects the curves in 3 different locations or more than one location. So we could not probably find a function y such that it depends on x. All right. Now, how do we go about solving this issue? If we kind of look at it from a little bit of bigger perspective, we see that, okay, the position of the ant on this surface, it kind of depends on another factor, which is time. As time progresses, the position of the ant changes. So it may be possible that we express x as a function of some other variable t, in this case time, and y as a function of time, y is equal to g of t. Now we might be able to express, we might be able to find the position of the ant as a function of time, where x and y are represented by 2 functions of time. Now, this representation is parametric representation. Now, the time t is called the parameter. And this set of equations is called parametric equations. And the curve it traces, which is this, is called parametric curve. Now, one point I'd like to make here is that in our context, the parameter is time, but it does not necessarily have to be time all the time. Depending on the scenario that you're dealing with, it could be some other factor or some other variable, okay? We use t here just to identify time. It could be anything else. Now, we trace the curve, okay, over some interval of t. So let's say a is less than equal to t is less than equal to b. So t is between a and b. So now my points x comma y, okay, at the initial point is going to be f of a comma g of a. So that's my initial point. And you could have a terminal point or ending point, x comma y, f of b comma g of b. Okay, so this is called the initial point and this is called the terminal point. Next, I'd like to give you a couple of examples of parametric equations, something very simple so that you can relate to it. So for example, let's say x is equal to cosine of t and y is equal to sine of t. What does it represent? It actually represents a circle. So if you have the Cartesian coordinate system, x, y, if you graph it, is gonna be a circle. It's a unit circle. Let me just show you how it works. If you square x, is going to be x square is equal to cosine square of t, right? cosine square of t. If you square y, you're going to get y square is equal to sine square of t. Now, if you add these two equations, you're going to get x square plus y square is equal to cosine square of t plus sine square of t, which is nothing but 1. So x square plus y square is equal to 1. This is something you already know. You have seen it before. This represents the unit circle, right? Now, parametric representation of unit circle is actually x is equal to cosine of t and y is equal to sine of t. And just to remind you, here t goes between 0 and 2 pi. 0 is less than equal to t is less than equal to 2 pi. Now, you may also have situations such as this: x is equal to cosine of 2t or y is equal to sine of 2t. Okay, what this does, it goes around the circle 2 times for this t interval, which is between 0 and 2 pi. But if you want it to go around the circle only once, all you have to do is change the interval for t. So it's gonna have to go between 0 and pi. T is less than equal to pi. Similarly, you could have cosine of 3t sine of 3t. In that case, if you keep this as an interval for t, is gonna go 3 times around the circle. But you could adjust your interval accordingly if you'd like to. In general, you could have cosine of nt, n is a positive integer, sine of nt. Okay, it'll go around the circle n times if you leave this. But this n does not have to be a positive integer. It could be a negative integer as well. It just will go in the counterclockwise direction. So that's what this set of equations represent. Now, let me give you another example. Let's consider that this is a wheel, okay, which is circular and is rolling, okay? So let's consider this point P on the wheel. As the wheel rotates, moves forward by rotation, this point P goes around the circle, right? What is the path? What path does it trace as it goes in circles? The path it traces looks like this, and this is called cycloid. This curve can be represented by a set of parametric equations. So let's consider this angle right here. Let's look here on this circle, and this angle, if we call it theta, okay? If we call it theta, so the parametric equations that's going to represent this cycloid is given by r times theta minus sine of theta, where r is the radius of the circle, right? The radius of the wheel, and y is equal to r times 1 minus cosine of theta. Okay? These two examples should give you some ideas of how we can use parametrization to represent a curve. And these are two nice examples to get you exposed to parametric equations and curves. I hope that this discussion was helpful. Thank you very much.